in Honduras, in the University of Honduras. And he's going to talk about Gravitino amplitude and stop. Wait. He's not going to talk? No, stop the case. Thank you.
Okay, good afternoon, everybody. It's really a tremendous honor to be here in this beautiful lecture hall. I would like to say thank you to the organizer for giving me this great opportunity to present my work. I'm going to talk about Gravitino amplitudes and stop decays. This work is in collaboration with Lorenzo Diaz-Cruz, that is also here. Okay, I'm going to start with the motivation that is basically physics beyond the standard model, searches for physics beyond the standard model. And then I will move quickly to Gravitino and Agostino interaction in order to compute Gravitino amplitude using the so-called new methods like the spin-orderlistic formalist for massive particles, and also I will show my last calculation using the trace technology, just to compare. And finally, some concluding remarks. Okay, my motivation is almost the same than the first lecture from last style, but let me remind you that we know that the standard model for particle physics is a very susceptible to friction of the phenomena at TeV scale. However, there are several open issues of the standard model that seem to call for new physics. Just to mention some of them are the hierarchy problem, and cannot unify gauge coupling, and also there is no dark matter candidate. So some natural candidate to theory to solve this problem is supersymmetry. That is a symmetry that unified boson with fermions, and it's also a unique extension of Poincare space-time symmetry. In supersymmetry, you can moderate the hierarchy problem, and let me point out that also provide a good candidate for dark matter. The basic idea is that in supersymmetry, or in this minimal supersymmetric standard model, you have for every boson of the standard model a super partner. That is, for example, take the gluons, you have the gluino, and the same idea is also true if you study the local version of supersymmetry. Gravity appears, and the super partner of the graviton is the gravitino. Let me say that within these SUSY models, the lightest supersymmetrical particle is a viable dark matter candidate, and if you want to study this model, the nature of the next to lightest supersymmetrical particle, because the LSP is stable and cannot decay, the next to lightest supersymmetric particle determines the supersymmetric phenomenology. So there are several candidates for the lightest supersymmetrical particle, and also for the next to the lightest supersymmetrical particle. The most popular choice is the neutralino for the LSP, but still another option is the gravitino. In this case, the gravitino is also a viable dark matter candidate. For the NLSP, there are also several candidates. I will point out the stop, the scalar top, the superpartner of the quark top, and each of these has its own distinct phenomenology. This has been studied for these people. Okay, so we can obtain the gravitino interaction in the minimal supersymmetric standard model as is usual. We can derive from the supergravity Lagrangian. You can take the best Baker textbooks. For example, the gravitino interaction with scalar fields can be derived from this Lagrangian, and also the gravitino interaction with the vector fields. So we are almost done. We can compute some observables. You have to keep in mind that the gravitino is a spin 3/2 particle, and in this model is a very weakly interacting particle, so a good candidate for dark matter. There is also this high energy equivalence theorem between the gravitino and the Agostino. That is, for example, the high energy limit, the spin 3/2 gravitino could be approximate to the Agostino. The Agostino is a Majorana spinor, so the Feynman rules are very easy compared with the Gravitino. So for technical reasons, people have been using the Agostino in this approximation. I will show some explicit calculation. For example, this channel, when the stop decay to the three-body, the stop decay, where the stop decay to the bottom, to the W, and to the Gravitino, you have to take into account these three Feynman diagrams. And you have here the vertices. This was first computed by Lorenzo and John Ellis. They approximate this vertex because, I suppose, for technical reasons. I will show you the complete calculation, and also I will compare with the Agostino approximation using the trace technology, as is usual in the quantum field theory courses in graduate programs in physics. For example, if you want to compute the observable, you have, using the trace technology, you have to square it and then average the amplitude. That's using the trace technology. But you can see here that, for example, when you have the Gravitino, the problem is that you have this tensor, and that is the completeness relation that is very huge. And even using Mathematica with the full simplification is very difficult. You have to separate all these traces. It's very involved to compute. Sorry. We have also a similar problem computing the interference of the diagrams, but sorry, it's not working. Okay, let me show you the final result using the trace technology for this three-body stop decay. Remember, this is the square amplitude. We want to have analytical expression in order to have control, but using the trace technology, you have huge expression as is usual. We would like to have a better techniques in order to compute Gravitino amplitudes. But even in this case, we can compare the three-body stop decay with the Gravitino in the final stage with the full calculation and the approximation that Ellis did with Lorenzo and also with the Agostino. You can see that for the low energy limit, or in other words, when the mass of the Gravitino is very low, the three decays are almost the same. We only, at this level, using trace technology, we only have comparison in the numerical analysis. We would like to have a better, as I said, a better method to compute that. So in the program of computing amplitude, you have to draw all the diagrams, write down the amplitudes. I would like to stop here. We can use the powerful method that flows from the amplitudes community, for example, the spinor elicit formalis, and you can avoid to square it. As you will see, this method is very powerful. Just let me show you very quickly what is the main idea of the spinor elicit formalis. Basically, you want to express the external moment of every particle in the interaction in terms of two-component spinors. This is for the massless case. So in other words, you want to express your amplitudes in terms of a better kinematical variables in order to improve your calculation and compute very fast and very efficiently. And you can read even in the Peskin, for example, this product of Dirac spinor, and when you replace by the two-component Weil spinor, you obtain that the momentum could be expressed as the product of two-component spinor. So the main idea is use this new for example, you can express this product that are the Lorentz invariant quantities in terms of these new, let's say, variables, and you use these new labels, for example, the square and angle product, and express all your amplitude using the traditional Feynman rules in terms of this product, and we already have all the new Feynman rules, for example, for the spinor, and also the polarization vector. You can notice that we are working at the beginning with the 2 degrees of freedom of the polarization vector. We are avoiding the redundance of use gates redundance in order to reduce the 2 degrees of freedom that the polarization vector has in traditional methods. This is called Chinese magic, was done for these people. So in order to compute, you have to use these basis identities. For example, the products are antisymmetric, and you can obtain the Magnus-Alkine variables just having this kind of product. Also, the reflection identity. Also, you have, for example, the first identity without any spinor indices, so it's very, very, very amazing. And also you have momentum conservation in terms of this spinor product. So if you want to see a very nice introduction, you can read the Lang-Dixon lecture. I think this is more new. Okay, but we want to compute amplitude with massive Gravitino. We also have the Feynman rules for massive particles. You can notice that something that is very nice is that you can express the spinor even when they have the mass in terms of this massless two-component spinor. So we can use all the amazing identities that we already showed for the massless case. The idea is very simple. You use Lie-Kohn decomposition in order to express a massive momenta in terms of 2 massless momenta, and we can, as I said, we can compute all the massive amplitude as massless, as I will show you. Okay, this started with the Meyer, and also you can read this paper from Stephen Weiser. Okay, let me do some checks in order to get confidence before I start with the Gravitino amplitudes. You can compute, for example, textbook's problem, or for example, take the Higgs decay to 2 fermions, build the amplitude using the traditional way at this level from the Lagrangian. You can build the amplitude, then use the spinor helicity formulas, and you can see that even in the massive case, we obtain helicity amplitude very compact. And after squaring, we reproduce the very well-known results. So very nice. We can have a more complicated Feynman diagrams with polarization vectors in the intermediate state. And still, we have very compact helicity amplitudes. And because all the properties of the spinor products, they are antisymmetric, etc., we can notice very quickly, even before to square the amplitude, the spurious degrees, let me say degrees of freedom, but in fact they are this helicity configuration. And again, we reproduce the very well-known results. So we can move to our problem and build the Gravitino or Feynman rules using these modern methods. And we already know that from the solution of the Rarita-Schwinger equation that there are 4 states for the Gravitino. And something that is very nice is that the Gravitino is expressed in terms of polarization vectors and spinors. And we already know how to express this quantities in terms of these new variables. So we can rewrite all the Gravitino's states in terms of these new variables, and then check some very well-known results from the literature. For example, this computation was first done by Jonathan Fenn, the neutralino decay to Gravitino and also to the photon. You can see that even in the massive case, the amplitudes, the helicity amplitude are very compact. For example, we only have these two configurations for helicity. This first column is the complete amplitude, that means the complete Gravitino, and this is considering the Goldstino approximation. You can see at this level that, for example, we obtain the correction for the Goldstino when we use the Gravitino. And for example, this pedagogical example that also is very nice. For example, when annihilation of positron and electron to Goldstino. For example, for the massless case, we only have these two configurations, but when we consider the mass of the particle, we obtain the same mass helicity amplitude with the correction of the mass, and also two new helicity amplitudes. So it's very nice. So let's come back to this old friend, the stop decays. The stop could be, there are three modes for the stop decays in this model with the Gravitino LSP in the final state. There is the two mode, the two decay, the three body, and the four body decay. This is the parameter space. You can see that even in the two body, of course, is the bigger one, but even for the four body stop decay, there is also a considerable region for the parameter space. So you can see now that, for example, if you compute the two body stop decay with the Gravitino with the massive Gravitino in the final state, we have at least in the two body stop decay very compact expression. You can see here in this column, for example, this is the amplitude. The C here, the capital C is just coupling constant. You can see, for example, that even with the total Gravitino, we have very small and compact expression. And something that is very nice at this level is that, for example, we found this regularization. Let's say that the amplitude with this Gravitino spin 3/2 in the final state could be expressed as this factor, data factor. By data here I mean this term that is just a function of the energy and the momentum of the external particles. So in terms of this amplitude with the Goldstino, as you can see here. So this is very nice, and it was impossible to notice using the trace technology. Okay, you can say this is at two levels. Let's say what's happening with three body stop decay that we already compute with the trace technology. This is really amazing. We only have this helicity amplitude. We found again this regularization that the amplitude with the Gravitino will be expressed in terms of the Goldstino approximation. Probably this is a result of the high energy equivalence between Gravitino and Goldstino, but again, it's very nice to notice at this level. And okay, can we compute the four body? Yes, it's even simpler than the three body, and we found the same regularization that the amplitude with the massive Gravitino could be expressed in terms of this. So you have to take into account that this amplitude in the left side is with spin 3/2, and this is when the spin 1/2, and that this helicity amplitude are still waiting to be squared. So all of this is at the level of helicity amplitude for the non-squared. Okay, now we can do some numerical analysis more efficiently with some non-fancy computer because our analytical results, and we can do, for example, the following statement. If for example, for the two-body stop decay, if you want to approximate the Gravitino to Agostino, it is good. If you want, for example, to have 1% of the accuracy, you have to work in this range for the mass of the Gravitino. In other case, you will take a bigger error in your calculation. This was possible just because our analytical refuel is in the spinolicity methods. This is, for example, in the three-body stop decay. This is the stop, the lifetime of the stop, and the excess is the mass of the Gravitino. For example, here, if you want to have accuracy of the 20%, this is the better you can do. You have to take the mass of the Gravitino among 160, between 100 and 65, more or less. In other cases, also your approximation is not good, so this could be a good result for cosmologists that are considering the Gravitino as a dark matter candidate. And for the four-body decay, we also do our analysis, numerical analysis. So the best you can do is if you want to approximate the Gravitino in the final state to Agostino, you have accuracy of 70%. So, but you have to take into account the mass of the Gravitino. So it's very nice to have this compact expression in terms of the mass of the Gravitino, because we made an improvement in our numerical analysis. So I know that everyone is tired, so let's summarize. So the spinolicity formalist allows to evaluate scattering amplitude incredibly simple and fast, even with the spin 3/2 Gravitino in the final state, and even if you have several legs in your Feynman diagrams, this is very amazing. So we could say now that a scenario with Gravitino as light supersymmetrical particle and stop as the next to light supersymmetrical particle was studied, and we did some improvement to the traditional calculation. And we have computed our commitment that was the time life of the stop before to decay, even to the four-body mode. So this is very amazing. It will have some implications in collider and cosmology. And as you see, we have compact relation between Gravitino and Agostino amplitude at the three level in this moment for the 2, 3, and 4-body stop decay. Thank you very much for your attention. Time for questions.
Thank you, Bryan. Thank you, Bryan. We have now a question.
So, very nice. I always learn something from you. So, regarding the spin 3/2 Gravitino,
Yes.
We looked at this 3/4 of a century old Veloz-Van-Siger problem, that the theory for a massive spin 3/2 particle is inconsistent because it has some non-causal, it has faster than light propagation when it has interaction. And my understanding of this matter is that for the Gravitino, this is fixed by supersymmetry. So supersymmetry protects it from developing these faster than light solutions. So the question is, in the way you're doing things, is there a role for supersymmetry in doing this? Or is this just because you're using non-redundant degrees of freedom? I mean, could this cure this Veloz-Van-Siger problem just because you don't have redundant? Because the origin of the Veloz-Van-Siger problem is that there is some ambiguity between the spin 1/2 degrees of freedom. It's sort of like 2 Poincaré orbits are getting mixed in a way that is not. So can you comment on this?
Okay, the method is very universal. You can use the spinolicity formally for massive particles for any theory, the standard model, as I already mentioned. But are you talking about the Gravitino and Agostino approximation, but
So I did not see anywhere where. So there are many ways in which these kind of problems manifest. So for example, you get the wrong poles in the propagator, or you get some. There are many ways to see that there can be inconsistencies. But the way this is done, it seems that no problem could develop. I was just wondering if you have maybe looked at. So for example, you can do this for the delta resonance in QCD, which is also spin 3/2. And
yes,
there are some questions as to how consistent is the description of the delta because of this, because in the way it's traditionally done, there are some problems. And maybe this, I think it's very interesting to think if this can be applied to that and sort of evade.
Yeah, it would be
this.
very nice if I could see the reference and then I could give a better answer.
Yes.
Tengo una pregunta.
Sí.
¿Qué efecto tiene este gravitino en la naturaleza o en el cuerpo humano? Puesto que se parece, los neutrinos no tienen ningún efecto nocivo sobre el cuerpo humano o sobre los objetos que atraviesa. Por favor.
Muchas gracias, es muy interesante la pregunta. Como dijo Andrés, voy a contestar en español. Si en estos modelos el gravitino se considera como un candidato a materia oscura, que es una materia que se dice oscura porque, digamos, no interactúa de manera no emite ni absorbe luz, que es algo que creemos es bastante aceptado en la comunidad científica, que de hecho el 27% aproximadamente de la materia del universo es materia oscura. Eso digamos que ya está bien establecido en la comunidad. Si el gravitino es realmente un candidato a ser materia oscura, esto pues sería increíble, porque de alguna manera sabemos qué partícula describe la materia oscura y tenemos control sobre ella. Y en ese sentido, la pregunta suya, ¿qué efectos tienen en la naturaleza? Pues sería interesante, el 27% de la materia del universo la tendríamos bajo control, por decirlo así. Y por el momento, no sé qué efectos tendrá sobre el cuerpo humano. Habría que ver primero si estamos rodeados de materia oscura. La Tierra está rodeada, eso creo que es algo que todavía no se sabe. Sí.
¿Qué relación tiene con los neutrinos?
Pues hay casos que sabemos que puede interactuar de alguna manera con neutrinos, es lo más que podríamos saber. O sea, digamos que matemáticamente sabemos cómo le habla uno al otro, pero no es que el gravitino, digamos, se comporte como un neutrino o viceversa. Sabemos nada más cómo podrían interactuar entre ellos. Sí.
One last question or comment? Yes.
Just a question, because you showed in very fine print the lifetimes of the stop, and it was all very long. And I was wondering, I was worried about cosmology and dumping a lot of energy into the universe through the decays after Big Bang nucleosynthesis.
You mean this, or
any of the plots? They were all, life 10 to the 6 seconds or longer, right? Everything. The lifetimes were all
yes.
10 to the 6 seconds or longer.
Yes.
And I was just curious, what are the constraints on the stop lifetime from things like when you put a lot of energy into the universe after Big Bang nucleosynthesis, there's a danger that it changes the abundance of the elements.
Yeah, I know that there are some bounds from cosmology, for example, the abundance of the relative density of the dark matter. There is also Big Bang nucleosynthesis, some bounds, but I don't remember I know from Collider that the stops has must to have bigger than 500 GeV from the Collider side, but from the cosmology, in fact, I think it could be very interesting to see what happens. Yeah.
Okay, thanks.
So I think that we have to close now. So we thank Bryan again. And so now we have, before we close,